Okay, so can you hear me? Okay, so today we're gonna see. So today we're gonna see. Uh, Today we're gonna see discussion. I mean question discussion from week 8 lectures, where the following topics have been covered. So the topics which are covered in this week are uh, Green's theorem and Gauss divergence theorem, and then Stokes theorem. And another is the uh, Gauss, sorry. Yeah, so yeah, I think these are the all three theorems that has been covered mainly. So we're gonna see some questions from all of this topic. So first, I'm gonna write the first question, which we'll be solving today. So this is question number 1. So the question is given as follows. Verify the Gauss divergence theorem for the vector field F equals to 4 4x I cap minus 2y square j cap plus z square k cap, and S is the surface, S is the surface bounding the region x square plus y square equals to 4, z equals to 0, and z equals to 3. Okay, so now we're gonna solve this question. This is just to verify the Gauss divergence theorem. So first we'll write the Gauss divergence theorem, and then we're gonna verify both the left hand side and the right hand side. Okay, so you're gonna do the solution step by step. So now what is Gauss divergence theorem? So it is written as follows. So this should be capital D. Okay, so let D be a closed and bounded region in the three-dimensional space whose boundary is piecewise smooth surface that is oriented in the outward direction. So that means the anti-clockwise direction. Okay, and so let the vector function defined as, or the vector field defined as v of x y z equals to, and v1 of x y z of I cap plus v2 of x y z of z cap plus v3 of x y z of k cap be a vector field. Okay, for which v1, v2 and v3 are continuous and its partial derivatives are uh, and have first order continuous partial derivatives. First order continuous partial derivatives. Okay, in some domain containing D, then the surface integration is changed into a volume integration over the region D, and then you take divergence and dx dy dz. Okay, so uh, Cost divergence theorem is all about a closed and bounded region. Okay, so basically you have a surface and this is enclosing a region D, and then the integration over the surface is same as integration like the triple integration inside the region D. Okay, but you have to just calculate the divergence. That's all. So here in cap where this vector n is the outward unit normal to S, or the outward normal vector uh, to S. Okay, so now we're gonna see all of this, or we're gonna be calculating all of this slowly. So, in our question, it was given that the surface is bounding the region x square plus y square equals to 4, z equals to 3, and z equals to 3. So z equals to 0 and z equals to 3. So that means this is a cylinder which is running from z equals to 0, that is the origin, to z equals to 3. So we can draw the surface, obviously, or maybe we can try to draw the surface. So this is gonna look like this. Okay. So this is our z axis. This is the x axis. And so suppose this is y-axis, or maybe this is y-axis and this is x-axis, and it is drawn like this. Okay, so this line is z equals to 3, and this point is obviously z equals to 0. And the equation of the cylinder is x square plus y square equals to 4. Okay, so now first we're going to calculate the divergence. So that means we're going to uh, compute the right hand side of this star. Okay, so first we compute the right hand side of star. Okay, which is the volume integration. Correct. So now what is divergence of B? So here B was here f was 4xi minus 2y square j plus z square of k. So the divergence of f will be 4i. So which is mm, so I mean not 4i, 4 minus 4y plus 2z. Correct. So this is our divergence of f, and we need this region D. Correct. So this RHS will be this integration over D, divergence of f dx dy and dz. Correct. So now here see that z is varying from 0 to 3. Correct. So this will be from 0 to 3, and our divergence of f is nothing but 4 minus 4y plus 2z. So this is 4 minus 4y plus 2z, and this is dx dy dz, and this is the region x square plus y square equals to 4. Okay, so this is gonna be 0 to 2 pi. So we're gonna change it to a polar coordinate. So r will vary from 0 to 2, z will vary from 0 to 3. Then this will be 4 minus 4r sine theta plus 2z into r dr d theta dz. Okay, so is this clear up to this step? Is there any doubt from this point, like up to this point? Okay, so if there is no doubt, then I'm moving forward. So first we're going to do the integration with respect to z. Okay, so this all has been taught in the week 8 classes. Okay, if you have not seen, you can go back to week 8 classes and then you can come back to this video again. So this will be integration 0 to 2 pi r equals to 0 to, so this will be theta 0 to 2, and this is 4 minus 4 r sine theta z plus z square 0 to 3 r dr g theta. Correct. So this is gonna be theta equals to 0 to 2 pi r equals to 0 to 2. So this will be 12 r minus 12 r square sine theta plus 9 dr d theta. Okay. So now we're gonna do the integration with respect to r, and then we'll do the integration with respect to theta, correct? So this will be from theta equals to 0 to 2 pi. So this will be 6r square minus 4r cube sine theta plus 9r. Okay, 0 to 2 d theta, and this is same as theta equals to 0 to 2 pi. So this will be 24 minus 32 sine theta plus 18 d theta. Okay, is this okay? Is there any doubt up to this point, or like anything from the previous one, like the previous page or anything? Okay, so this is gonna be, so this will be 42 theta plus 32 cos theta 0 to 2 pi, right? So this will be 84 pi, and I think this will be 0. So this will be 84 pi. So for the right hand side, that is for the volume integration, it should be 84 pi. Now, since we are verifying the Gauss divergence theorem, so similarly for the surface integration, this value also should be 84 pi, correct? So now you see that our surface was like this: x square plus y square equals to 4, z equals to 0, and z equals to 3, correct? So it was like this, correct? Okay. So now we can see that this whole surface can be divided into three surfaces. So let us call it as uh, this one as S1, this one as S2, and this one as S3. Okay. So now we have to calculate this surface integration. Surface over S f dot n ds, right? Okay. So now first try to see that for this curved surface S2, we have to calculate this n, correct? So for the curved surface S2, our n is nothing but, or maybe we can write, so yeah. So this is norm of or gradient of f divided by norm of gradient of f. Okay. So here f of xyz is x square plus y square minus 4 equals to 0. So gradient of f is 2x I cap plus 2y j cap. Okay. So our n cap will be 2x I cap plus 2y j cap divided by square root of 4x square plus 4y square, correct? And this is just 2x I cap plus 2y j cap, and then x square plus y square equals to 4. So this will be square root of 16, which is just 4. So this will be 1 by 2 x I cap plus y j cap. Okay. So now here our ds is dx dot dy divided by n dot k, or ds equals to dx dot dy by n dot I, or ds equals to dx dot dy by n dot j. So since we cannot project this integration to this region to the xy plane, because in this case z will be k, this n will be k. Okay, so then this n dot k, in this case it will be 0, because here in n there is no k cap, so n is just 1 by 2 xi cap plus yj cap. So since there is no k component, so if you take n dot k, it will be 0. Okay, and we don't want this, right? Otherwise this integration won't be implementable. So that's why we're gonna project onto the yz plane. Okay, so you can also project into the xz plane, and both are same thing. So we'll take d of s2 equals to dx dot dy divided by n cap dot I cap. Since we are projecting onto the yz plane, so it will be I cap, and this is same as sorry, this will be dy dz. Okay, so dy dz by x by 2, because n is 1 by 2 into xi plus yj, so n dot I will be just x by 2. Okay, so this is our thing, and this is same as 2 dy dz by square root of 4 minus y square, because x square plus y square equals to 4, so x will be just square root of 4 minus y square. Okay, so for this surface S2, our integration will be changed into over, so again we have to compute f dot n. So this was our f, and this is n cap. So what was f? F was, so f was this one, 4x I cap minus 2y square j cap plus z square k cap. So this will be 4x I cap minus 2y square j cap plus z square k cap dot product with, this is 1 by 2 xi plus yj. Okay, and this is same as 2x squared minus y cube. Okay, so our surface integration f dot n cap d of s2, this is changed into over s2, this is 2x square minus y cube, which is f dot n, and then ds is just 2 dy dz by x. Okay, so now this will be just, so here x square plus y square was 4, z equals to 0, and z equals to 3. Okay, so we take x equals to 2 cos t, y equals to 2 sin t, where t will range from 0 to 2 pi. So this integration will be changed to this is over z equals to 0 to 3, because 0 less equals to z less equals to 3, t equals to 0 to 2 pi. Okay, and 2 into 2 cos t whole square minus 2 sin t whole cube, and then 2 dy dz divided by x. So 2 into 4 cos t sin t, sorry. So dx will be minus 2 sin t, and dy will be, sorry, dy will be 2 cos t dt. So this will be 4 cos t dt dz divided by 2 cos t. Okay, because there is a division of x, so that's why x is 2 cos t. So here x is 2 cos t. So this is z equals to 0 to 3 and t equals to 0 to 2 pi. Okay, so this is 8 cos square of t minus 8 sine cube of t, 4 cos t, 2 cos t got cancelled out, so this will be 2 dt dz. Okay, so this is same as 16 times 0 to 3, 0 to 2 pi, 1 plus cos 2t by 2 minus 3 sin t minus sine of 3t divided by 4 dt dt. Okay, so this will be 16 times 0 to 3, and this will be t plus sine 2t by 2 divided by 2 minus so this will be cos 3t divided by 3 minus 3 cos t divided by 4. Okay, and this will be from 0 to 2 pi. Okay, so now if you just calculate all of this, it will come as 0 to 3 dz, and this is same as 48 pi. Okay, so this is just straightforward integration, so you can verify all of this calculation. Okay, so there is not any rocket science here. So now this is for the surface S2. So this one we are done. So now we have to calculate for the surface S3 and S1, correct? So for the surface S1, and see that x square plus y square is 4 and z is 0, correct? So here here actually our z is 0, right? Because z is varying from 0 to 3. So that's why here our n is minus of k, because we have to take outward unit normal. So this will be our n cap, which is just minus of k cap, because this is our k cap. So that's why for the surface S1, the outward unit normal vector will be just minus of k cap. And then f dot n will be just z square, which is 0. So over the surface integration, f dot n ds is 0. Okay, now we have to calculate for the surface S2, sorry, S3. Okay, so here for the surface S3, so we can see for the surface our z is 3, because z is varying from 0 to 3, correct? So in this surface, x square plus y square is 4 and z equals to 3. Correct. So our n cap is just the k cap, and f dot n cap is z square. And this is just 3 square equals to 9. Okay, and our ds is uh, dx dy by n dot k, and this is dx dy by k dot k. So this is just dx dy. Okay, then the surface integration over ds1 is just over s1, and this is 9, and then dx dy. Okay, this is just n into double integration s1 dx dy, and this is just n into area of s1, which is same as area of the circle x square plus y square equals to 4. So this is just n into pi into 2 square. So this is 36 pi. Okay. So the whole surface integration over S is changed into 48 pi. So this is like over S1 uh, f dot n ds1 over S2 f dot n ds2 plus over S3 f dot n d of S3. So for S1 this is 36 pi. For S2 this is 48 pi, and for S3 this is 0. So total is 84 pi, and this is same as the right hand side. Okay, so the Gauss divergence theorem is verified. Okay, so I hope this is clear now. So now we're gonna go to the next question, which is question number 2. Verify Stokes theorem for minus y square of z of k cap, and C is the circle x square plus y square equals to 1, uh, corresponding to the surface of sphere of radius 1. Okay. So first, we're gonna write the Stokes theorem, and then we're gonna verify both the left hand side and right hand side for this question. So Stokes theorem. Uh, let S be a piecewise smooth orientable surface bounded by piecewise smooth simple closed curve C, and let the vector field V be this one be a vector field for which V1, V2, and V3 are continuous and have continuous first order partial derivatives in some domain containing S. Okay. If C is traversed in the positive direction, so that means in the anti-clockwise direction, uh, then this line integration over C on C is same as this surface integration. Okay, where n cap is the outward unit normal vector to S in the direction of orientation of C. Okay, so now so I think this theorem was already stated in these week classes. So suppose S is a piecewise smooth surface bounded by a piecewise smooth simple closed curve C, and then a vector field if V is defined in which both all V1, V2, V3 are continuous and have their partial derivative continuous, first order partial derivative continuous in some domain containing the surface S, and then this line integration over C is just the curl of V dot n cap over the surface S. I mean, you just perform the surface integration over S as provided this curl V or dot n is computed. Okay, where n is taken as outward unit normal vector to S in the direction of C. Like for example, if you take C in the positive direction, and then you have to take the n cap also in the direction of C. Okay. So now our F was given like this. Mm, 2x minus y into I cap minus yz squared j cap minus y squared of z k cap. Okay. And x squared plus y squared was 1. So first we're going to calculate the right hand side of star. So first we'll calculate the right hand side of star. Okay. So for that reason, first we're going to calculate the curl of F. So this will be I j k cap del del x del del y del del z 2x minus y minus of yz square and minus of y square of z. So this will be I cap minus of 2yz plus of 2yz minus of c cap 0 minus 0 plus k cap 0 plus 1. Okay, so this is just k cap. So the right hand side of star is just the surface integration over S curl F dot NDS. Okay, so now since here curl F is coming as K, so we can take on the projection onto the XY plane. So that means here K dot n cap or K dot n cap into Tx dy divided by K dot n dot K. Okay, and this get cancel out. So this is just the surface integration of Tx dy. So now here the surface is just the projection onto the xy plane, and which is x square plus y square equals to 1. Okay, so this is just pi into 1 square and pi. Okay, so RHS is just pi. So now to calculate the line integration over C, it was given that C is the circle x square plus y square equals to 1. Okay, so now we can parameterize the curve as follows. So RT equals to cos t I cap plus sin t j cap, right? Plus 0 into k cap, well 0 less equals to t less equals to 2 pi. So our LHS, which is integration over C f dot dr. So this can be written as 0 to 2 pi. So this will be dr by dt and then dot dt. So it can be written as 2 cos t minus sin t into minus of sin t, because z is 0. So all other terms will be 0, and this is dt. Okay, so this is just 0 to 2 pi minus sine 2t plus sine square of 2 dt. Okay, and this can be written as 0 to 2 pi minus sine 2t plus 1 minus cos 2t divided by 2 dt. Okay, so this is cos 2t by 2 plus t by 2 minus sine 2t by 4 and 0 to 2 pi. So this is just 1 by 2. I mean, this is 1 by 2 plus pi minus 0 minus 1. Uh, sorry, this is pi by 2. This is 1 by 2 plus pi plus 0 minus 1. So this is minus 0. Sorry. So this will be 1 by 2 plus pi minus 0 minus 1 by 2 minus 0 plus. So this is just pi. Okay. And already we have calculated our right hand side as pi, right? So here. So this is equals to right hand side of star. Okay. So I hope this is clear. Please go through the video again if you have any doubts, or go through the notes which will be available on the site. And I hope this will be clear. Okay. This is not that difficult. So you have to do some more practices, and then we'll be good to go. So now we're gonna do the next question. Okay. So verify Stokes theorem for if cap equals to 2y I cap minus xj cap plus 3y k cap, and C is just the cylinder x square plus y square equals to 9 and z equals to x plus 3, oriented in the counterclockwise direction. Okay. So first you're gonna calculate this right hand side, that is the curl of v dot in dot n, and then the surface integration, and then we're gonna calculate the line integration. Okay. So here our curl f is this ijk del del x del del y del del z, and this is 2y minus x and 3y. So this is just 3 minus 0 minus of z 0 plus of k. This is minus 1 minus of 2. So this is 3i minus of 3k. Okay. And our if x, y, z is given by z minus x minus 3. Okay. This is equals to 0. So our n cap will be gradient of f by norm of gradient of f. So this is just minus of I plus 0z plus k cap divided by square root of 2. Okay. So call f dot n cap. So this is gonna be minus 3 by root 2 minus 3 by root 2. So this is just minus of 3 root 2. Okay. And our ds is dx dy by n dot k cap. So we are taking the projection onto the xy plane, which is just this circle, x square plus y square equals to 9. Okay. So this will be dx dy divided by what is n? N is minus 1 by root 2. Sorry, 1 by root 2 minus of I plus of k cap. So this will be just 1 by root 2. So root 2 dx dy. Okay. So this is surface integration over S. Call f dot n cap ds. So this is just integration over S. This is minus of 3 root 2 into root 2 dx dy. So this is minus of 6 over S dx dy. So here our surface is just the projection. I mean, this is not the S, this is the projection R, which is x square plus y square equals to 9. So this will be minus 6 times pi into 9. So this will be minus of 54 pi. Okay. So yeah, this is the answer for the surface integration. Okay, so now we're gonna calculate the line integration. So the curve is defined as x square plus y square equals to 9 and z equals to x plus 3. Okay. Now the parametric form is written as follows: rt equals to 3 cos t I cap plus 3 sin t j cap, and this is z of k cap, which is just 3 sin t, sorry, 3 cos t plus 3 k, where 0 less equals to t less equals to 2 pi. Okay. So now f dot tr, this is just so what was f? So F was this 6 cos t 6 cos t I cap minus 3 cos t j cap plus 9 sin t k cap, and dot product of minus 3 sin t I cap plus 3 cos t j cap minus of 3 sin t k cap. Okay, so this will be sin t. So minus of 18 sin square of t minus of 9 cos square of t minus 27 sin square of t. Okay, so this is minus of 9 minus of 36 sin square of t. So this is minus of 9 minus of 18, 1 minus cos of 2t. So this is minus of 27 plus 18 cos 2t. Okay, so now this line integration. So this is from 0 to 2 pi minus of 27 plus 18 cos of 2t dt. So this is minus 27 of t plus 18 sine of 2t by 2. This is 0 to 2 pi. This is minus 54 pi plus 0. So this is just minus 54 pi. Okay, and this is same as RHS. So this Stokes theorem uh, is verified. Okay, so I hope this is clear now. Okay, so now we're gonna write the next question. Let f equals to z square of I cap plus xyz cap minus y square of k cap, and s is the portion of the surface of cylinder 36 and 0 that's equals to z that's equals to included in the first octant then calculate the value of the surface integration. Okay. Okay. So the surface is just the cylinder. This is drawn as follows. Okay. So the projection will be this line. Uh, this is subradius 6, and z is varying from 0 to 4. So our fxyz is x square plus y square minus 36. So our n cap will be 2x I cap plus 2y j cap divided by 4x square plus 4y square, and this is same as 2x I cap plus 2y j cap divided by square root of 4 into 36. So this is 2 times xi plus yj divided by 12. So this is 1 by 6 xi plus yj. Okay. And then if dot n cap, this is just x z square by 6 plus xy square by 6. So this is x time z square plus y square by 6. Okay. And our ds is so so now here we can see that we cannot take projection onto the xy plane because there is no k component on it. So then our ds will be undefined. So that's why we'll be taking projection onto the yz plane. So this will be dx dy, sorry, mm, dy dz by n dot I. So this is just dy dz by x by 6. Okay. So our surface integration over S f dot n ds. So this is just x time z square plus y square by 6 dy dz by x by 6. So this is just z square plus y square dy dz. So now we are taking the projection onto the yz plane. So in the yz plane, x is 0. So the equation was uh, 0 x square plus y square equals to 36, and 0 less equals to z less equals to 4. So if you put x equals to 0, then y square will be 36. Okay, and y will be plus minus 6. But we are taking only the integration. I mean, we're taking the region only in the first octave. So y will be positive. So this will be just between 0 and 6. Okay, so this will be our the projected R. So this will be just a rectangle. Ty. This is z square plus y square. Ty dz. So z equals to 0 to 4, y equals to 0 to 6, z squared plus y squared dy dz. Okay, so this will be from z equals to 0 to 4, z square of y plus y cube by 3, 0 to 6 digit. This is same as z equals to 0 to 4, 6z square plus, so this will be 36 into 2, so this is 72 digit. Okay, so this is 2z cube plus 72z 0 to 4, so this is just 128 plus 72 into 4 is 8. So, so this is 288. This is 416. Okay, so this should be the answer. Okay, so now we're gonna move on to the next question, which is question number 5. Verify the Green's theorem for the vector field f equals to x square minus y cube into I cap plus x plus y into j cap. Okay. Uh, so here C is the closed path containing x plus y equals to 0, x square plus y square equals to 16, and y equals to x in the first and fourth quadrant. Okay. So first we're gonna write the Green's theorem. So let C be a piecewise smooth, simple closed curve uh, bounding a region R if m n uh, del f del y and del n del x are continuous on R, then m dx plus n dy uh, is is equal to the double integration over R, and we have to calculate del n del x minus del m del y. Okay, so this is like Green's theorem connects the line integration to the double integration. So it connects as follows. So if there is a closed region and which like has a boundary C, then it connects to the inside of that region. I mean that inside region of the curve, like the interior of the curve, and then it performs the integration on the interior of this region, which is called as R here. So it connects the boundary to the interior of the region by performing this double integration. Okay. So here C is x plus y equals to 0, x square plus y square equals to 16, and x equals to y. So now we're gonna draw the region first, and then we're gonna verify both the left hand side and the right hand side of this star. So first we draw the line y equals to x. So this is the line y equals to x, and x plus y equals to 0 implies y is minus x. So this line is y equals to minus x, and then x square plus y square equals to 16. Okay, so this is x square plus y square equals to 16. So now if you put y equals to x in x square plus y square equals to 16, so this will be 2x square equals to 16, or x equals to plus minus 2 root 2. Okay, so so the region is given by this one. Okay, so so let us call this as C1, this as C2, and this as C3, and this region is R. Okay, so now for C1, so for this region C1, we can see y is minus of x, correct? So the parametric equation will be just minus of sorry, t of y minus t of j, where 0 less equals to t less equals to 2 pi. Okay, and here t is varying from 0 to minus of 2 root 2, or 0 to 2 root 2. Okay, because x is 2 root 2 imply y is minus 2 root 2, so this will be minus plus 2 root 2, because y was minus x. So this integration over c1 f dot dr, so this will be from t equals to 0 to 2 root 2, and f was x square minus y cube, so this will be t square minus t square plus t cube, because y equals to minus x, I cap plus x plus y, so this will be t minus t of j cap, dot ti minus tj dt. So this is 0 to 2, and then sorry, this will be dti minus dtj. So this will be t squared plus t cube dt. Okay. So this is t cube by 3 plus t to the power 4 by 4, 0 to 2 root 2. So 2 root 2 whole cube by 3 plus 2 root 2 whole to the power 4 divided by 4. So this is 16 root 2 by 3 and plus 16 multiplied by 4 by 4. So this is 16 root 2 by 13, 3 plus 16. Okay. So now for C2, so for C2 we can see the line is y equals to uh, sorry. So for C2 R of t is 4 cos t I cap plus 4 sin t j cap, where t is from minus pi by 4 to pi by 4, because for this line C2 it is this value of t is ranging from here to here. Okay, and this angle is just pi by 4 because y is x, so this implies theta is tan inverse of 1, which is pi by 4, and similarly here theta is tan inverse of minus 1, this is minus pi by 4. So this is gonna be integration over C2 f dot tr equals to minus pi by 4 to pi by 4, and then x square minus y cube. So 16 cos square of t minus 64 sine cube of t I cap plus 4 cos t plus 4 sine t j cap, and then dot product with minus 4 sine t dt into I cap plus 4 cos t dt into j cap, and this is from minus pi by 4 to pi by 4. So this will be minus of 64 cos square of t sine t plus 256 sine to the power 4t plus 16 cos square of t plus 16 sine t cos t dt. Okay. Now if you just do a little bit of calculation, this integration value is just 52 pi minus 120. Okay. So now for C3 curve, y was x. Okay. So this will be r of t will be ti plus tj, where So this will be minus 2 less equals to t less equals to 0. Okay, and then C3 f dot dr, and this will be same as from minus 2 to 0 t square minus t cube I cap plus t j cap dot product with dt of I plus dt of j. Okay, and this is same as minus 2 to 0 t square minus t cube dt t square minus t cube plus 2t dt. So this is t cube by 3 minus t to the power 4 by 4 plus t square. This is minus 2 to 0. This is minus 16 root 2 by 3, and this will be 16 to 4 by 4 plus 8. Sorry, minus of 8. So this will be for all positive, not negative. So yeah, now it's okay. So now this will be minus of 16 root 2 by 3 plus 16 minus 8. So this is minus of 16 root 2 by 3 plus 8. Okay, so our total integration value will be integration of C f dot pr equals to over C1 f dot pr plus over C2 f dot tr plus over C3 f dot tr. So this is 16 root 2 by 3 plus 16 minus of 16 root 2 by 3 plus 8 plus 54 pi minus 100 of 20. And this is same as 54 of pi minus 96. Okay, so this is the value of the line integration. So now we can verify the right hand side, that is the double integration on the region R. So the region looks like this. Okay, so this will be del n del x minus del m del y dx dy. So our m was x square minus y cube and n was x plus y. So our m was x square minus y cube, n was x plus y, and del n del x is just 1, and del m del y is just minus of 3y square. So this will be 1 plus 3y square over this region R. Oh, sorry, is dx dy. So this will be theta from minus of pi by 4 to 5 by 4. So R will vary from 0 to 4 because the radius was 4 of that circle. And this will be 1 plus 3r square sine square of theta r dr d theta. Okay, so this is from minus pi by 4 to pi by 4. This is r square by 2 plus 3 r to the power 4 by 4 sine square of theta d theta, and r will vary from 0 to 4. So this is from minus pi by 4 to pi by 4, and this is so 8 minus of 192, sorry, plus of 192 sine square of theta d theta. Okay, so this is 8 theta uh, plus 96 into theta minus sine 2 theta by 2, because you just multiply 2 and divide by 2, then 2 times sine square theta can be written as 1 minus cos 2 theta by 2, 1 minus cos 2 theta, and then you do the integration. Okay, so this is gonna be 8 pi by 4, uh, so sorry, so one time calculation is gonna be 8 pi by 2 plus 96 pi by 2 minus of 96 by 2, 1 plus 1. So since this minus of sine 2 theta is an odd function, even function, so this will be 2 times all multiplied. So that's why this is gonna be 52 pi minus of 96, and this is the same as LHS of star. Okay, so I hope this is clear. This is just basic integration. There is not any complicated integration. You could verify all the calculations again. So if this question is correct, this answer should be okay. So now we're gonna move on to the next question, which is question number 6. So let C be the uh, boundary of the region enclosed by y equals to x square and y equals to x. Then calculate the value of the integral. X cos hyperbolic 2y into y cap plus 2x squared sine hyperbolic 2y into j cap dot dr. Okay, so so clearly this is an application of the Green's theorem. So we can change this line integration to the double integration. Correct. So first we're going to draw the region in which we're going to perform the double integration. So try to see that. So this region is bounded by y equals to x square and y equals to x. So so this line is y equals to x, and so this point is 1, 1. Okay, and the region is bounded by this one. Okay, so by Chris theorem, uh, this indication is changed to this double indication over the region R. Okay, so this is over R, del del x of 2x square sine hyperbolic 2y minus del del y of x cos hyperbolic 2y. Okay, so this is 0 to 1, and then the x strip is going to be from the y strip is going to be from x squared to x. So this is x squared to x, and this is just 4x sine hyperbolic 2y. So this will be minus of 2x sine hyperbolic 2y. So this is same as 0 to 1 x squared to x 2x sine hyperbolic 2y dx dy. Okay, so this is 0 to 1, and then cos hyperbolic 2y by 2, and this is x squared to x dx. So 0 to 1, and cos hyperbolic 2x cos hyperbolic 2x minus of cos hyperbolic x squared by 2 dx. Okay, so this is 0 to 1 x cos hyperbolic 2x minus of x cos hyperbolic 2x square dx. So now we can multiply by 4 and divide by 4. So this is gonna be x sine. So we can perform the integration of uv. So this will be u integration v minus plus v integration u minus v integration u. So this will be x sine hyperbolic of 2x divided by 2 minus cos hyperbolic of 2x, and this is minus of sine hyperbolic 2x squared by 4. Okay, so this is from 0 to 1. So this is using integration of uv dx, u integration p dx minus p integration u dx, and uh, so now this is just sine hyperbolic 2 divided by 4 minus of cos hyperbolic 2 divided by 4 plus 1 by 4. Okay, so this is the answer of this question. So I hope this is clear now. So please go through the video again if you have any doubts, and then you can let me know. So now you're gonna go to the next question, which is question number 7. So find the surface area of the portion of the paraboloid z equals to 2 minus x square minus y square that lies above the xy plane. Okay, so we know the formula as s equals to double integration over r square root of 1 plus zx square plus zy square uh, dx dy. Okay, so here zx is del z del x, which is just minus of 2x. Zy is del z del y, which is minus of 2y, and then square root of 1 plus zx square plus zy square is 1 plus 4x square plus 4y square. So s equals to double integration over r square root of 1 plus 4 times x square plus y square dy dx, and this is same as 0 to 2 pi 0 to root 2 1 plus 4r square r dr d theta, and this is same as integration 0 to 2 pi 1 plus 4r square whole to the power 3 by 2 by 3 by 2 0 to root 2 1 by 8 d theta. So this is 1 by 12 27 minus 1 d theta. Okay, and this is 0 to 2 pi. So 26 by 12 into 2 pi. So this is the so 1 by 2 pi into 26 into 2 pi. So this is 13 pi by 3. So yeah, this should be the answer. Okay, so I hope this is clear. So now we're gonna go to the next question, which is question number 8, and it is given as follows: find out the surface area of the portion of the sphere x square plus y square plus z square equals to 9 lying inside this cylinder x square plus y square equals to 3y. Okay, so here since we know the formula, which is double integration square root of 1 plus zx square plus 1 zy square, and here z is square root of 9 minus x square minus y square. Correct. So gx is gonna be 1 by 2 square root of 9 minus x square minus y square into minus of 2x. Okay. This is minus of x by square root of 9 minus x square minus y square. Similarly, gy is also minus of y by square root of 9 minus x square minus y square. So square root of 1 plus zx square plus zy square is square root of 1 plus x square by 9 minus x square minus y square plus y square by 9 minus x square minus y square. And this is same as square root of 9 divided by 9 minus x square minus of y square. So this is just 3 divided by square root of 9 minus x square minus y square. Okay. So here x square plus y square is 3y and x square plus y square is 9. Okay. So the first circle is this bigger circle. This is 3 comma 0. And this one is x square plus y square minus 2 into 3 by 2 into y plus 9 by 4 minus 9 by 4 equals to 0. So this is x square plus y minus 3 by 2 square equals to 3 by 2 square. Okay. So this is somewhere here. Okay. So r square is 3r sine theta or r equals to 3 sine theta. Okay. Hence this surface integration is over this 1 plus over r 1 plus zx square plus zy square dx dy. This is changed from 0 to 3, 0 to 3 sine theta, and sorry, this will be 0 to pi. So this is because we are taking here from the first and second octave. So this will be square root of 3 divided by square root of 9 minus r square, r here 3 theta. Okay. So 3 0 to pi, and then 9 minus of r square to the power 1 by 2 1 by 2 and 2 minus of 2 0 to 3 sine theta. Okay. So this is minus of 3 0 to pi. This will be 3 cos theta minus of 3 d theta. So this is 9 1 minus plus theta minus sine theta 0 to pi. So this is just 9 pi. Okay. So yeah, this should be the answer of this question. So I hope this is clear now. So now we're going to go into the next question, which is question number 9. Let f equals to 2x plus z to the power 3 by 2 I cap plus 3y minus exponential of z square j cap plus x cube plus y cube to the power 4 by 3 k cap, and S is the uh, boundary of the region G uh, below the paraboloid z equals to 4 minus x square minus y square. Inside the cylinder, x square plus y square equals to 1, and above the xy plane. Uh, Calculate the value of surface integration f dot n d sigma where n cap is the unit normal vector. Okay. Okay. So we're gonna solve this using the Gauss divergence theorem, because the Gauss divergence theorem connects the surface integration to the volume integration. I mean, just but the regions would be closed and bounded region, right? So by Gauss divergence theorem, we obtain. So first, we'll calculate the divergence of f. So this is gonna be just 2 plus 3 plus 0, which is 5. So this surface integration f dot n cap d sigma, this is changed into the volume integration divergence of f dv. Okay, and this is same as now z is varying from 0 to 4 minus x square minus y square. So this will be z equals to 0 to r square. I mean, sorry, 4 minus r square in the parametric form. In the polar form, theta will vary from 0 to 2 pi, and r will vary from 0 to 1. And this will be 5r tz tr d theta. So theta is 0 to 2 pi, r is 0 to 1, and then z will be 0 to 4 minus r square. So 5r 4 minus r square here d theta. Okay, so this is same as theta equals to 0 to 2 pi, and r equals to 0 to 1, 20r minus 5 of r cube dr d theta. Okay, so theta is 0 to 2 pi, and then this is 10 r square minus 5 by 4 to the power 4, 0 to 1 d theta. So this is 2 pi multiplied by 10 minus 5 by 4. So this is 2 pi multiplied by 35 by 4, and this is 35 pi by 2. So yeah, this should be the answer of this question. So I hope this is clear now, and so let me explain it again, what I have done here. So the question is given like this, that F is a vector field where S is the boundary of the region G below the paraboloid Z equals to 4 minus x square minus y square, and inside the cylinder x square plus y square equals to 1. Okay, so the paraboloid looks like this. So Z is 4 minus x square minus y square. So if you put x and y 0, then Z will be 4. Okay, so this will be a downward paraboloid. Sorry. So this is Z, this is x, this is y. Okay, because if you put x and y to be 0, then Z will be 4. So so this is the paraboloid, and inside the cylinder x square plus y square equals to 1. Okay, and the projection of the cylinder will be something like this. So this is x square plus y square equals to 1. So now what we did is we use the Gauss divergence theorem. So then the enclosed region will be changed into a volume integration. Okay, so this is by Gauss divergence theorem. This is changed to divergence of f dv over the region V, and here V is varying from 0 to 4 minus r square, and so the cylinder will look like also this, and this is a circle. So okay, and so here Z will vary from 0 to 4 minus r square, and then this enclosed region is bounded and closed and bounded. So by divergence theorem, so this is just uh, divergence of f dv, and dv is just varying from 0 to 4 minus r square. This is 4. So this is, so this z is just 4 minus x square minus y square. Okay, so then it will be z equals to 0 to 4 minus r square, and the projection onto the xy plane will be just x square plus y square equals to 1. So that's why r is 0 to 1 and theta is 0 to pi 2 pi, and the divergence is just 5. So using the change of variable, it will be 5 r dz dr d theta, and then if you do the simple integration, then you will get the answer as 335 pi by 2. So I hope this is clear how this is done actually, because this region will be bounded from here to here. Okay, somewhere here. So that's why this region is closed and bounded, because the above there is a paraboloid. Uh, okay, so now let us solve the next question, which is also an application of the Green's theorem. And the question is written as follows. So let C be the unit circle x square plus y square equals to 1, oriented counterclockwise, evaluate this line integration x square minus y dx plus y square plus x dy. Okay. So this is a example, or this is an application of the Green's theorem. So we have to just apply the Green's theorem on the region, on the unit circle. So here, I mean, just inside the unit circle. So here the region is like this. Okay. So this is the unit circle x square plus y square equals to 1. So now using Green's theorem, we have, so let us call it as a star. So then we can see that M is x square minus y, and N is y square plus x. So by Green's theorem, this star is equals to, this is the integration over d, and then uh, del n del x minus del m del y into t. So now del n del x is just 1, and del m del y is also minus 1. So this double integration is just this integration over d, and then 1 minus minus of 1 dA. Okay, this is 2 dA. And since the region d is just the unit circle here, and also the inside of the unit circle, so here we can put the area of the unit circle as 2 into pi into 1 square, because the region is inside this unit circle. Okay. So this is our d. So hence the answer should be 2 pi. So integration over c x square minus y dx plus y square plus x dy equals to 2 pi. So I hope this is clear now, and you can solve also some questions from exercise of some books, some standard books, and then concepts will be more clearer to you. So yeah, thank you for bearing with me in this course. So I served as a TA to discuss this questions from this respective week classes, and I hope you enjoyed it as well as I enjoyed. And Yeah, see you in the next course. If I